Welcome you all guys for this session. In this we have previously studied a bar subjected to a point load, and we applied the Rayleigh-Ritz method, and we found out the displacement of the system. And here we will be taking one more example where we will be applying the same bar subjected to a tractional force or a surface force. So this is a different example. The only thing difference here is the load. Okay, so in the previous case we have seen a point load, and now we are taking a surface load. So if you see the problem definition, the body is been having a length A, cross section area A, length L and cross section area A, and modulus of elasticity E, subjected to a distributed load T is equal to X, Cx, okay, where C is the constant. So we need to determine the displacement of the body. So same procedure we need to apply here. First we need to write the potential energy function, and then we have to write the displacement function. So here first we will start with the problem definition. So first step of the Rayleigh-Ritz method is that you have to formulate the potential energy function. Okay, so that is pi is equal to strain energy plus work potential. As it is a bar, which we know that as it is a bar, we have a common strain energy which you have solved in the last class. So strain energy for bar is given as AE by 2 integration 0 to L dou U by dou X the whole square into dx. So this is the strain energy for bar. So you have to write now work potential. Okay, now carefully see here. This is a distributed load. Distributed load means the load acting on a certain length, okay, or overall length. So if you can see that it is not acting at a particular point, it is acting over the axis. Okay, throughout the axis it has been acted, and it is a distributed load, so it becomes a surface force. So we have already seen how to calculate the work potential for a distributed load or for a surface load. So whenever a surface load comes, we used to write integration 0 to S T into U into ds. This was the way we need to write the work potential. So now as we are doing a 1D analysis, we are interested in 1D analysis, and the load is acting over the length. It is not acting over the area, it is acting over the length. So we will convert this for a lengthwise load. Okay, so what is the conversion? So we will be converting it as 0 to over the length it is acting from 0 to L. So it is, we will be converting it to L. So now we will be writing it as T into U. What is the parameter which is the important parameter for the load here is the length, and it is along the x axis, and it is go on applying along the length. So it becomes T into U into dx. So like this formula converts. So previously we converted it as a area, so we have to take it as a surface area, the load applied on the surface area. Now it is applied over a line or over a length. Okay, we are just converting it, that is integration 0 to L T into U into, the variable was ds here, the variable now is dx. Okay, so this is the work potential, and you have to apply negative sign as work is the load is applied, or the work done is on the system. So this will be the work potential and this will be the strain energy. So we will combine them to form an equation, that is AE by 2 integration 0 to L dou U by dou X the whole square into dx minus integration of 0 to L T into U into dx. Like this we can write. So but if you see in the problem definition, they have given what is the T value. T is a constant into X. So I will just substitute that. So you will be getting it as AE by 2 integration 0 to L dou U by dou X the whole square into dx minus integration 0 to L t is nothing but c into x, or I'll write it as c into u into x into dx. Okay, x into dx. So this is the potential energy functional equation when it is subjected to a distributed load. Now you have finished the first step. So now we'll move on to the second step. The second step says that you have to assume a displacement function. So same way, the same logic will be applying. Okay, the second step says that assume the displacement, assume the displacement model, assume the displacement model. Okay, so how the displacement model will be applying, we'll be using algebraic displacement model. So we need to see the boundary conditions. So first boundary condition, basically the boundary conditions as we have discussed is being divided into two types. One is the displacement constraints, one is the loading constraints. So if you see what are the displacement constraint, one end is being fixed, so this will be 0, which means I know one constraint. Second is the load is applied over a particular length, so I know the second constraint, there is a load applied is there. So I have only two constraints. So from the model I will be choosing u is equal to a naught plus a1 x. Okay, see whenever you are choosing the displacement model, it is an assumptions which we are just taking it. Okay, sometimes the displacement model might be wrong, and you need to take the higher order like x square, x cube, or x raised to 4. You need to take it, but for this simple problem, if you see only two constraints are there, we can easily take it as a two constants. If two or more constraints are there, you need to go for the higher order polynomials. Okay, so this is u is equal to a naught plus a1x. So now what I'll do is I'll applying boundary conditions. Applying boundary conditions. What are the boundary conditions we know? We know only one boundary conditions, that at x is equal to 0, u is equal to 0, because in the previous problem there was a point load here acting. So because of this load there was a displacement happening. As here the overall body is being subjected to a distributed load, we can't take it that as a boundary conditions. Boundary conditions will be only the end conditions. So from here what is happening, from this end what is happening, I don't know what is happening in this end, I know only what is happening in this particular end which is being fixed. So I'll take only this boundary condition. So at x is equal to 0, u is equal to 0. So if I apply u is equal to 0 and x is equal to 0, so I'll get a naught is equal to 0. So I got one constant value here. I got one constant value. So next what I'll do, I'll use this constant and substitute in the what do you call it as principle of minimum potential energy functional. I'll be just substituting in pi equation and try to find out the value of a1. Okay, so for substituting, what all the things we need to just go through this. So first what we need is, if you just go on with this equation, I need dou u by dou x. Okay, and also I need what is u. So if you see from this particular equation, u will be what, a naught is 0, u will be a1x. A naught is 0, already we calculated, we got u is equal to a1x. So next what I'll do, I'll be finding the value of dou u by dou x. So what is dou u by dou x? U is a1x, its differentiation with respect to x will be a1. Okay, I hope it is clear. So next we will be just substituting the values of these into the principal potential energy functional. So what I'll do is I'll just rub this out, or I'll just rub this out. I hope you have taken this. I'll just rub this out. I need this bottom equation. I'll just keep it as it is. The third, substituting displacement function in potential energy functional. potential energy functional. Okay, so I'm just substituting this. So I'll write once again this equation, then I will be substituting the values. So what is this? Phi is equal to AE by 2 integration 0 to L dou U by dou X the whole square into dx minus integration 0 to L C U x into dx. So this is the equation. So wherever the values are there, I will be substituting. In du by dou x, we will be substituting a1, and wherever u is there, I will be substituting it as a1x. So I'll just write it down. So it is ae by 2 integration 0 to L. So this is dou u by dou x, it becomes a1 square into dx minus integration 0 to L C. Okay, what is u? U is a1, x is there, x into x becomes x square into dx. Okay, so this is how we have substituted. So I hope it is clear. I have just on dou u by dou x I have substituted a1, it is square, and wherever u was there I have just substituted as a1 x. X was already there, it becomes x square. So next we will solve this and we will simplify it. So if you see here, it is ae by 2 integration 0 to L a1 square. So integration of dx becomes x. Sorry, I have to just stop this. I am doing it integration. So a1 square into x 0 to L. Okay, so minus this integration becomes c a1 x square becomes x cube by 3. It becomes 0 to L. Okay, so this is how we do the integration. So what will remain here is ae by 2 a1 square into x becomes the limits, if you put it becomes L here, minus c a1, it becomes L cube by 3, L cube by 3, because L, the limit is 0 to L. Okay, now we got the value as pi is equal to ae by 2 a1 square L minus c a1 L cube by 3. So next step will be minimizing the potential energy function. So fourth step is minimizing the potential energy functional. So how to do that? So how many unknown parameters you are there, you have to see. This is already a constant term, this is only the term which we need to find out. So what I will do is dou pi by dou a1 should be equal to 0. Dou pi by dou a1 should be equal to 0. I will just rub this part. And we'll do the differentiation of this. So 0 on one side, dou pi by dou a2, I will be differentiating it. So ae by 2 into a1 square is there, its differentiation becomes 2a1l minus, okay, so a1 is there, it becomes c l cube by 3. a1 differentiation becomes 1, okay, so it becomes c l cube by 3. So now we will be doing we will be finding out the value of a1 here. So what you will get, c l cube by 3 will be equal to ae l into a1, okay, so l gets cancelled, so it becomes c l square by 3 equal to a1 ae. So a1 will be equal to CL square divided by 3AE. So A1 will be equal to CL square upon 3AE. I'll just check out whether it is correct. Yeah, this is right. So finally we need to find out the value of displacement. So what is the displacement equation we had got? So if you just see the previous equations, we had an equation called as AU is equal to U is equal to A naught plus A1x. Okay, so we got the value of A naught as 0. So U was A1x. So what is the value of U will be now? It becomes CL square divided by 3AE 3AE into x. So this was the problem definition. So we need to determine the displacement of the bar at the end. So at the end means, so you can take at x is equal to L. At x is equal to L. End means this end. At x is equal to L, what you will be getting? U is equal to C L. If I multiply here, it becomes CL cube divided by 3AE. CL cube divided by 3AE. So this, whatever the boundary condition are there, so we can verify that whether the displacement function whatever we have taken, it is right or wrong by seeing the displacement equation. If you see this displacement equation, we need to fulfill all the boundary conditions, that is the displacement boundary conditions. So first, if I apply this same equation, if I apply the first boundary condition at x is equal to 0, if I take at x is equal to 0, what will be the displacement equation? You should get 0. You should get 0, that is CL square 3I is the constant term here. If I multiply x as substitute x as 0, the u becomes 0 here, and the other term at u is equal at x is equal to L, you will be getting this value. So this satisfies the boundary conditions, and it indicates that the whatever the displacement function you have assumed will be correct. Okay, so this is the problem with respect to the surface load. So I hope it is clear. So in the next assignment, I'll be just giving a problem which will be I'll be giving a notes which will indicate if a body is subjected to a body force. Okay, I've taught you guys if a body is subjected to point load and surface force. If a body is subjected to a body force, what will be the equation? So you need to calculate that in the assignment part. So I'll be giving you that same body which is subjected to a body force, which means it is subjected to its own weight. How to calculate the value of displacement? So same formula comes, only thing for the work potential, okay, you have to apply the work potential because of the body force, where volume has to be considered, and that volume has to be converted into area and dx, which you have done for the bar strain energy of the bar, how you have converted V into A into dx, the same thing you have to apply for this. Okay, hope it is clear. Thank you.